Hello everybody. Welcome to Positron, Electron, Chicken or Egg. Welcome this 12th of October 2025. Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So how is everyone today? I had the pleasure of growing up with chickens at our house. And I used to like to imitate them. You know, sometimes my parents would ask me to go and wring the neck of one so that we could have it for dinner. You know, that's a thing. How is everyone? Okay, I've got some going over Wi-Fi. My computer decided to upgrade to Windows 11, unfortunately. And it's lost the wireless, rather the wired connection. So I'm going to see if I can fix that, get it a bit faster, because I think it's going to be not very good. You probably hear my audio. Okay. Why are you using Windows, Bob? It's a good question. I don't want to do this unless it's going to be smooth. So let's just see if, no, it's still looking a bit glitchy. Yeah, okay. I hate to window that. I might need to restart somehow and find a solution to this. Oh, lovely. Yes, it's definitely glitchy. In fact, it's saying no data. Don't know how that's worked. Now it's saying excellent connection, but it's not. Is it smooth? Oh dear. It's not going to restart, Weird Nerd, because it is physically not remembering how to connect to the network via network. It seems to have forgotten that. Yes, it's a little bit glitchy. Okay, I might have to start again. I'll leave the connection open and I'll try and fix the data. So when the recording's done, it'll just be a break. I'm very sorry. This is very important. I do want to go over it. So let's I'll break this and I'll come back. Okay. Okay, I'll try and keep it open, but it wasn't that I chickened out. I do think I've got enough data now. It's saying upload 24.53 megabytes, and it was the router. For some reason, it had got its knickers in a twist, and it wasn't working as we should hope it should. Okay, hopefully that hasn't disrupted my thought train. Yeah, so where was I? I was saying I grew up with chickens. I used to like to imitate them, and sometimes we have this phrase in English, which is referred to as being a chicken, which is to say, I won't do something because I'm fearful of a negative outcome. Okay? For those that thought I was going to solve the age-old problem of which came first, the chicken or egg, well, everyone knows it's the egg, so that's pointless. And so hopefully this should be good. Is everyone able to Yon Does Life says, you calling me a chicken? No, I'm not. Hello, Ken Pratt. Hello, John L. Hello, username. Hello, Weed Nerd. Hello, David Ellis. Spirit Life Space. Hello, Zalapino. Hello, Alex Lozman. It's great to have you here, Gordon Doherty and Contraptions. Very, very good quorum in the house. Sorry, we lost about 30 people. Oh, but they've just popped back. We've got 51 in the house, so this is all very good. Okay, so what are we talking about today? We are talking about a paper that has been published on 7th of October 2025, and it was published in Physical Review X, and it is called Experimental Signatures of New Channel of the Deuteron-Deuteron Reaction at Very Low Energy. And it has many people I know personally, and all of these people I have met. Of course, one down here, one Mathieu Velat, is a former founding, well, always, a founding director of the Martin Fleischmann Memorial Project. And so he is the last named author. The Rakesh Dubey, I think it is the first named author. And Konrad Chersky is the head of one of the two European-funded mega projects for looking into our field. And over here we have Natalia Targash-Slechka, and I have fond memories of her in, I think, 2022, when I was talking about cavitation being the simplest way to produce these effects. And I talked about Kladoff, and I talked about cavitation-based heating systems, and about the hydrowave technology, I think it is, in Russia for remediating biological and chemical weapons. And I started that presentation off by saying something like, does anyone know what a toroidal moment is? And there was silence in the room. And then I said, does anyone know what an anapole is? And Natalia said, an apple? I said, yeah. So she made a joke. It was quite funny. And yeah, so that is our cast of characters here. And this is a key data point in their presentation. But before we go there, I want to talk to you about shame and humiliation and put downs and so forth. But before we do that, here is what you need to know. So if you do not watch any of the rest of this presentation, I want you to go and look up this paper, Experimental Signatures of New Channel of the Deuteron-Deuteron Reaction at Very Low Energy. You will need to get this reference here, HTTPS, and this one here, this reference here. This is what you'll need to get. And I want you to do something for me, and that is to talk about it in your social media. So there you go. That's Rakesh's email. It's publicly listed. I'm not doxing him. It's just publicly listed here. Okay. And get this link and comment, putting that link and experimental signatures of new channel of whatever you want to put, but make sure you include this link, okay, in there. Now, why am I saying that? Well, the aim of the MFMP was to first see if we could replicate it, second to see if we could find out how the process is working, and third, that is to help promote it in all its guises, whatever this thing is that we got involved in back in 2012. So, what am I asking you to do? Well, if you go to Altimetric here, you can see this paper here. This is the way that it's tracked out there in YouTube's land, and people can see the sort of effect that it's having out there. And this has got an attention score of 6. You can see here we go. We've got the same authors here. It's the same name. It is that paper. Okay. And you can see after the 7th, it had a little bit of interest. And then by the 9th, it had flatlined. This is not good for our field. We want people to be looking at papers in our field now that the European Union has actually taken a chance and funded some of this. And one of the groups which was headquartered here in this city, up at Brno University of Technology, they didn't actually produce any research experiments. They did produce some papers, but basically, in my view, they were essentially meaningless. That chunk of the 11.7 million euros was basically wasted. Now, the other group, they have done several papers which are interesting, and this, I think, is the cream of the crop for the conclusion of that project. And so I think we need to give it a big shout out. And so what do we want it to look like? Now, I haven't asked anyone to promote the paper that I did with Binjuan Huang, but this is where we want it to kind of be. And I think we can do this. And the way Altimetric is working, it's looking for engaged users on YouTube and Reddit and Facebook pages. So these are the places I want you to get out there. X users, a blog, a news outlet. And so it would be good for you to, you know, get out there and, like, if everyone could use their X, and maybe you're a YouTube creator and you can send a news article out or a note out on YouTube or on your Facebook. Maybe you've got a Reddit connection and you can go and open a discussion up on Reddit. That will start to get it some attention. So, you know, that's basically what we want to get it doing, right? So this is a call out for you. This doesn't really cost you anything, but it gets eyes on the subject. And so there we go. Now, this actual work here is essentially to do with electron screening, okay? And actually, it's also obviously to do with a so-called lattice effect basic. If you don't have a metal solid structure for the process to occur, you don't have the metals to provide the electron screening to provide the enhanced reaction ratios. That's the whole theory as how it goes. Now, when I was in Morioka in Japan, I had prepared, I'd rented at my own expense with the donations that were raised out of doing the book, a side sort of venue next to the main presentation room in Morioka. And there was, in that, basically people had to come out of that room, go down a corridor down the side of that main presentation room and walk past the venue that I had rented, where it was all open glass and you could clearly see what it was, right? It had been promoted by by Haslan Back of Engate, and I had printed flyers and posters and I'd handed them out to everyone. And I wanted people in Japan to come and see what Matsumoto had done, and particularly things that I had been able to pull out of his dataset using modern scanning technology and brought into the modern era. I wanted them to see the beauty of the way he worked, which is unique in the field at the time, and it's really groundbreaking what he found. Anyway, not one Japanese person outside of particular people I know, particularly Sho, came to watch that. I did see many Japanese people walking past the room to go to the toilet. And so that was shocking, but I was not surprised because Sho told me beforehand, we're in one of the fancier hotels. We couldn't afford to stay there, but we'd been invited by Roger Green to go and have breakfast at his expense. Thank you, Roger. At this particular hotel where he was staying. And we went in there and it was a fabulous spread. And Sho had come as well because he was staying in our hotel. And he said, I've just spoken to Kazagi. He knew Matsumoto. Why don't you go and sit with him? He's all alone over there. And who am I referring to? I'm referring to this character. And he's called Hirota Kazagi, and he is on the solid state fusion site here, which is a project, I believe, that is supported by one Carl Page, who's been very generous to the field, sponsoring different organizations. And he's a very friendly chap. And I know him pretty well. He's always been very gracious to me. And you can see here that he is the Professor Emeritus at Tohoku University. And look at this, 301 publications, 25,400 reads in total here on, what's this, ResearchGate, is it? ResearchGate, which is about, as we looked the other day, I think the paper by Stephen E. Jones on the event had been read something like 70,000 times. So for one paper, 301 publications have been read 25,000 times. But that isn't the important metric here. The important metric here is this, 3,571 citations. That is really good. That's a very high number of citations for a number of publications. You're looking like 100 plus on average, okay? So Hirota Kasagi, I sat down with him and I said, Dr. Kasagi, I said, I'm preparing a presentation for a guy I think you knew. And my colleague says you knew him and I would very much like you to come. His name is Dr. Takaaki Matsumoto. And he said, yeah, he had some silly ideas. I nearly choked on my miso soup. I nearly choked on my miso soup. One of the most prominent researchers in this field in Japan completely mocked the work of Dr. Takaaki Matsumoto. So I didn't hold out much hope, and I always have zero expectations of anything happening, so you're never disappointed. But it did not surprise me. Given his prominence, Mr. Kasagi's prominence in the field, and his reaction to me saying that I was going to be giving a memorial presentation and showing some of Matsumoto's work brought from the abilities of scanning in the early 1990s into the modern scanning from his negatives. No, not interested. Not interested. He had silly ideas. Okay? So what does Kasagi think low-energy nuclear reactions are about? Well, here is one of his famous papers here. And it's been cited 6 times. It's a low ratio. But it's kind of the thing he's thinking about here. So of particular interest is the fact that reaction rate of DD reactions at 2.5 kilo electron volts, that's very low energy, in PDD is 60 times, and in PD 10 times, that's PD oxide, palladium oxide is 60 times, and in palladium is 10 times larger than in titanium. And the deduced screening energy, okay, so he is dealing with screening energy, okay, amounts to 600 EV, brackets 300 EV for, I guess, straight palladium. So palladium oxide is better than palladium. You get 600 or 300 EV. Furthermore, the subsequent study in lithium plus D reactions showed large screening energy as higher effectively as 1.7 keV. So that's a lot higher than 300 EV or 600 EV. This is 1.7 keV. These cannot be explained by bound electron screening, which may give at most an energy of 20 EV for DD reaction of 0.3 keV, and for lithium deuterium. Okay, so basically he's talking about solid reactions and screening energy. Okay, screening energy. That is his focus. Why would that be a problem for someone thinking about Matsumoto? Well, how can Matsumoto create one-point cold fusion like this, producing synthesis of matter, which is a completely different element to the starting element, and it's definitely not a fusion That's carbon coming out of a lead ball. This is silly. The fact that we have replicated it independently before I knew about Matsumoto, doesn't matter. The fact that we've literally replicated the experiment 71 doesn't matter. And you know what? We replicated it on the first try. On the first try. Okay? But it's silly because in DD fusion, you can't possibly having lead turn to this. You can't have that turn to that. Okay? So just forget it. This isn't happening. You can't see it. It's not there. Right. So back to the subject in question here. It is this paper. Now, I reached out to the authors of this paper and including my former co-director of the project, Matthew Villatte. And firstly, Rakesh Dubey replied to me, and then Konrad Chersky replied to me. I asked specific questions. I then asked specific follow-up questions in both cases, and I got, well, I'll read you what I got. But essentially, I felt a little bit like Matsumoto should have felt had he been sitting opposite Mr. Kazagi. Yeah, okay. All right. So just bear with me a second. Okay. So whilst you're waiting for me, please go out onto your socials and promote this paper. That would really be a good thing to do. Okay. Because I have so many windows open here. I know it's here somewhere. Okay. So. Oh, and by the way, before I gave this presentation, I also gave them the heads up that I would be looking at this paper tonight. Now, Matthew had an old email which I emailed him on, so he didn't respond until after I'd had these two interchanges with the authors. So I said, well done, guys, in what appears to be your wonderful proof of the late Dr. Taka Matsumoto's E plus E minus de-excitation explanation for DD fusion branching in metal, as published in Fusion Technology, Volume 18, 1990, submitted 26th of February, 1990. I immediately recognized it when I read the link to your paper Matthew sent me. So Matthew sent me within hours of it being published. I went to look at the paper immediately. I was meant to go to bed. It was nearly midnight. I went to look at it, and I immediately saw what I recognized from Matsumoto's work. To the best of my ability, skim reading and remembering back. I have attached a copy of his paper, which is part of the book I am remastering. I will tell his family that his ideas have been further verified. We verified his one-point cold fusion work recently also. What a genius, so ahead of his time. Shame he could not see all this validation when he was alive. What impressed me most about him is that he read all other research papers, very rare in this field. And so I gave a link to the replication. I said this was the experiment that I suggested to all of the authors in this paper in 2020, years ago in Assisi, 2022. You get to see the whole electronuclear collapse process and regeneration inside an hour. It was really fun to be able to show the whole experiment to not only members of the public, but also to Matsumoto's daughter and one of his grandsons, who is not even born when the original experiment was done over 27 years ago. I may be wrong, but you might want to check blah, blah, blah. Okay. And I was wrong about what I just said about the thing. There was an NG on there, but it's yeah. Anyway, so Konrad Chersky replied, "Dear Bob, what we observe in our experiments is not an iton particle proposed by Matsumoto or Nato. The internal E plus E minus pair creation is a standard electromagnetic transition in nuclei. Only difference is that in 4-helium we observe the 0 plus threshold resonance, which is responsible for an enhancement of DD fusion at extremely low energies. We could previously observe the resonance in the proton channel. This channel is, however, weaker compared to the E plus E minus channel, which results from a special cluster, deutero-deuteron, in structure of this resonance. So everything we have presented is in agreement with standard nuclear physics." So I replied and I asked some questions. I said, would you say that your E plus E minus would mark radiographic emulsions in the same way? Because I referred to a separate paper where Matsumoto showed these tracks, and I'll show you them. The track goes across the emulsion and then it splits into 2 angles opposite each other practically. And this is what Matsumoto says, is that the iton, which I'll explain what it is, travels across the emulsion and then it decays, releasing a positron and an electron. And I asked a whole bunch of questions. How can you know that the beam deuteron interacting with the 2D is not working with this process? How can you differentiate the E plus E minus is produced from your pathway for he excited than his? What radiographic emulsion work have you done to physically demonstrate your hypothesis? How does your process explain large clusters and their breakup products he observed repeatedly in radiographic emulsion and other witness materials that we have also observed? How does your theory explain other fusion and fission products seen across LENR, particularly both lighter and heavier element synthesis at the same time? His theory explains it well. How can your theory explain large amounts of matter disappearance inside samples? How does your theory seamlessly transition to complete matter collapse and rebirth as we and other researchers observed? How does your theory explain large structures of transmuted elements and long-lived plasmoid production as he, Shoulders, Klimov, Urskev, Adamenko, Bogdanovich, etc. and ourselves have observed? And I said that I would be, in due course, publishing a promotion piece on your team's work, and I think it would be helpful to have your team's answers to the above. So Rakesh, the principal author, then replied, "Dear Bob, before starting a detailed discussion, I would like to make our point of discussion here very clear and simple. Let's try to understand DD fusion in a metallic environment at thermal energy." So that is what they're framing. All they wanted to do is to try and understand DD fusion in metallic environment at thermal energy. So they are saying this is only for in a metallic environment. Only. Okay? It's only at thermal energy. And it's only for DD fusion. There's no other reactions going on. We're only interested in what happens in DD fusion. Okay, that's right. That's okay to frame something. If we start including many general or even exciting observations from cold fusion field, it becomes a never-ending story. Some of you might agree. In our paper, we have already mentioned our experimental procedure, and so far we have followed nearly the same method in all our accelerator-induced fusion experiments. I have CC'd in my university email address on this message as well. Please use it for future correspondence, as I do not check this email address regularly. So I asked a whole bunch of other questions with context, which I will give, and Konrad Chersky came back. So I didn't get any answers. Konrad Chersky came back after a second series of questions and said, "Dear Bob, from the perspective of nuclear physics, Matsumoto's hypothesis is merely an improvised idea, devoid of any theoretical or experimental justification. Nothing. No experiment justification at all. No, none of it. It's just a hypothesis. It's just an improvised idea. The observations of ion tracks, as well as other experiments he mentioned, could have many different explanations. There is no evidence to suggest the existence of new elementary particles. Such particles, if they exist, should be observed in many other nuclear experiments." That's not what he did. He did not specify what mass, spin, and parity we should expect, or what interactions the new particle should participate in. In our case, the electron screening effect is very well established in many physical fields and documented in many experiments involving different nuclear systems. We understand how we can change its strength and increase the reaction rates. The E plus E channel was also observed in many different reactions before. As previously said, in the case of helium-4, this channel is much stronger than the proton channel because of the threshold resonance that was early observed. Our study focuses exclusively on the DD reaction in metal environments. We do not intend to explain all the effects you mentioned in your email. However, I believe this is sufficiently ambitious. So we're not interested in anything else. We're only looking at metal and DD fusion. Actually it just says DD reaction in metallic environments. Okay. So I said, Dear Conrad, here is the download link to Matsumoto's first book. He never published his second book. I have answered your commentary in below. Bear with me on this. I'm going to go through the paper specifically and relate it to these things in a minute. It's going to be tough. That's why I came out with the promotion at the beginning. From the perspective of nuclear physics. Okay, I'm just dealing with that from, and probably I might need to just, I'm not going to show it. From the perspective of nuclear physics, so Conrad is saying, like, you might talk about Matsumoto and whatever else nonsense that you go on about, but from the perspective of nuclear physics is how he opens his email. I said to him, Matsumoto was a consummate professional nuclear scientist all his life. For decades before 1989, he had worked with experimental nuclear reactors on linear accelerators and cyclotrons all over the world, making practical experiments to test theory. His special expertise was in nuclear emulsions, and he knew what was emitted from standard nuclear reactions and how they appeared on the emulsions. It is a tragedy that this expertise is not in the field currently. The next part of Conrad's comment was, Matsumoto's hypothesis is merely an improvised idea, devoid of any theoretical or experimental justification. I said, not true. He had a theory to explain a radically altered branching ratio favoring an aneutronic, gamma-missing, and 4-helium pathway as the primary reaction of what was then called cold fusion. He ran calculations. It produced data. He ran experiments. It produced data. And his comparison of the two led to the conclusion, which included the proposal that the iton, a stand-in abbreviation for what was at best a quasi-particle, and one option that he suggested to explain the data, including 511 keV photons, was that it was a positron-electron pair. So I will show you the data. He shows the de-excitation from the DD fusion to the 4-helium star excited state is de-excited via a thing that he had a stand-in name for called an iton. And he said that it could possibly be an electron-positron pair that then releases the energy. It carries away the energy. Conrad says, the observations for ion tracks, as well as other experiments he mentioned, could have very different explanations. It's true. I said, this is true. It is also true to say that if one does not ever expose any nuclear emulsions in the correct way, accounting for the capabilities of the emulsions you expect, the emissions you expect, and do not do any proper statistical analysis of these tracks against controls, thank you very much, Black Toe, for that £20, against controls, not finding anything because you don't look doesn't mean one conclude nothing was there. Someone that thought they had a superior interpretive skill based on better understanding of nuclear physics that you know may be able to look at the data he gives in his publications freely available at the link above and give an alternative explanation. Perhaps if they gave this data and calculations a good look, they might come to the conclusion he was onto something. Again, not looking at his body of work is not the same as knowing it has no merit. He looked at the angles of a decaying something on his emulsions against controls and concluded that it was evidence of a decaying something that produced a positron-electron pair. He then goes on to say, this is Conrad, there is no evidence to suggest the existence of a new elementary particle. And I reply, a meson in the form of quark-antiquark is a composite particle. He suggests that the iton could be an positron and electron, or that it could include a neutrino. If you read through his nuclear equations, there is the necessity for the neutrino in the paths proposed. Particularly, in experiment, you can only detect the decay on emulsion and the positron-electron annihilation gammas. If you do not use emulsions, you can only make the hypothesis from the positron and electron annihilation gammas. He proposes that the reaction's energetic D would lead to standard kinetic fusion reactions, accounting for observations of those. I'll explain what that means later, but essentially, what Conrad is saying is you've got a bunch of deuterons in a titanium piece of metal prepared by my colleague and friend, former co-director of the project, Matthew Villatte, and you fire a beam of deuterons in it at a specific energy, say 10 or 20 kiloelectron volts, and it goes in. There is a resonance. I would imagine you could think that as in my view, the way I see that is the de Broglie wave of the deuteron is resonant with a resonant mode of the deuteron in the metal lattice, such that with the screening energy, it allows for it to fuse at a higher ratio than would normally occur. And basically, the tritium and the helium path out are normally 50-50, basically, and the 4 helium path normally from DD fusion is 7 orders of magnitude. That's 10 to the power 7 less likely than the other two, okay? So basically it doesn't exist normally, but the branching ratio is much higher in these systems, and this is the attempt to try and explain what's going on. So they're saying that when the deuteron coming into the deuterated titanium goes in there, there is a reaction that causes DD fusion to 4 helium, but it's got 23.78 or whatever it is, mega electron volts, can't remember offhand, excitation energy, and that normally comes out as a gamma, but you don't see the gamma. So he's saying that the gamma does internal pair production, which he calls internal pair creation, and that takes away the energy from the reaction, de-exciting the nucleus down. In Matsumoto's work, and I'm going to show you it, he says you have a hydrogen catalyzed fusion. So you already have deuterium in a metal surface or at the crystal grain boundary. Your deuteron, extra deuteron, comes in and it forms a triple nuclei interreaction. And there's an electron crushing effect going on, and ultimately that causes the fusion, and there is an iton created. The iton is an electron, positron, and a neutrino. I'll explain how that occurs. And it results in the 4 helium plus a D, a little d. And the little d comes out at high speed, and interacts with another deuteron and produces the standard fusion reaction products. So this is what I'm saying, and I'll show you with the various papers. This is where is the the positron and the electron coming out in the de-excitation, and that's all there is, and there is other normal reactions going on, or is it that the other reactions come after? So the bit where the primary reaction is the primary reaction is going to 4 helium. Anyway, okay. So so he says if such particles exist, they should be observed in many nuclear experiments. David Ellis, yes, damn the naysayers, but this is very good work. It's very good work, but I think it needs to be, some additional work needs to be done, and I'm coming to that. Such particles, if they exist, should be observed in many other nuclear experiments. And I followed that by saying, no one in the field of condensed matter nuclear scientists, and practically no one in the modern field of nuclear research of any type, has any experience with nuclear emulsions or interpreting them based on decades of prior use studying normal fusion and fission processes. For the field of condensed matter nuclear science, I confirmed this immense and lamentable inadequacy during my presentation in Strasbourg. And if you, again, if you can't look for something, does not mean it's not there. That is to say, if you don't or can't look for something, it does not mean it is not there. Thank you very much, Black Tie. And then he goes on. Conrad goes on. He says, he did not specify what mass. And I replied, he did. And it was in the last paragraphs of the first paper I sent you. He said the mass was between 2 masses of electron and 26 times the mass of electron. He did not specify the spin and parity we should expect. I said, Conrad, regarding spin, his tables showing the composite particle permutations on the second paper I sent you allow the reader with basic knowledge of spin to calculate the possible outcomes. Regarding parity, need I mention the parity violation of beta processes? Of course, there is a fudge, the vector minus axial vector for that, right? So there's a problem when normal beta processes occur. You can go and look at it up on your favorite AI of choice, and it's the beta parity violation. And they came up with this kind of like way to get around this problem, which is used in modern mainstream physics. Then he goes on, or what interactions the new particles should participate in. And I reply, he goes into great detail to explain the interactions and how they occur and the products. From a compression, one can imagine an itonic mesh wanting to crush something more than a bunch of electrons alone. I'll explain this later, but essentially, how you get an iton is a bunch of electrons become so intense that they polarize a proton. There's a proton in a hydrogen, there's a proton in a deuteron. Okay, so protium and deuterium both have protons in them. So they get polarized, and out comes from that proton is like the opposite of a neutron decaying. So a neutron would decay into a proton, electron, and an antineutrino. In this case, the forced decay of a proton produces not an electron, but it produces a positron. Not an antineutrino, but a neutrino. So, and you get left with a neutron. Okay? So, read my lips again. The electrons in a cluster force the proton in either protium or deuterium to be polarized, forcing it to emit a positron and a neutrino. In a similar way, an analogous way to when a neutron decays, a free neutron decays into a proton, electron, and antineutrino. So what you get out of the system is a neutron from the proton, a positron, and a neutrino, and there's already an electron there associated with the original proton in the original atomic hydrogen or deuterium. Okay, the positron and the electron bind in a similar way to the meson that's made of a quark, an antiquark, and it's just a kind of, this is an idea, this is a speculative idea on his part, but it's not based in nothing because he observed these tracks of these things breaking up. And that structure, because it has a positron there, it becomes an itonic mesh. And if this happens with tens of thousands, if not millions or trillions of nuclei at the same time in this electron cluster, it crushes it. These positrons come out. They go into the itonic mesh, which is predominantly electrons. But the positrons and the neutrino in there assist in crushing because the positron wants to come next to the electron and annihilate it. So it helps in the crushing process. And because you've got a neutron, the neutron can it can pass through all the other matter because it's neutral, right? There's no charge repulsion, so it can go into the core more. And so that's the whole kind of basis behind the kind of crushing process that he discusses. Now, of course, I have a different view on this, but that doesn't matter. I'm just saying, like, you need to think about these processes that other authors have proposed and not just dismiss them because you haven't looked. So I say, from a compression, nuclear reaction and physical, optical and scanning electron microscopy viewpoint. So he's not just looked at blips on a radiation monitor. He's not just looked at that. He's looked at it on a nuclear reaction basis, on a physical, optical, what you can see under the microscope, and he's looked at it on nuclear emulsions and on scanning electron microscopy. So Conrad goes on. In our case, the electron screening effect is very well established and in many physical fields and documented in many experiments involving different nuclear systems. We understand how we can change its strength and increase the reaction rates. And I answer, I am not dismissing this. We should all primarily want to find the best ways to practical technology. I know I do, and keep an open mind. I said, for instance, like Edmund Storms, it was an honour to witness him swallow his pride and say that he considered electron clusters are responsible for all LENR reactions. That was at ICCF 26. Moreover, I like that he credited Ken Shoulders as offering an explanation for how electron clusters can form. Matsumoto in 2001, after his book was published, in a note to fusion technology, also gave credit to Ken Shoulders, but had believed that the EVO was too ill-defined for some time, since 2004, I think, 5. I agree with Matsumoto, but I don't think Ken didn't have a better explanation, just that he could not publish it. But furthermore, it only became clear to me why, after ICCF 26, firstly in 1995, Matsumoto was prevented by a deliberate change in the rules in fusion technology run by George H. Miley from publishing more in fusion technology. He protested against it. Matsumoto and Shoulders both referred to their collective ideas as ball lightning. In 1995, a patent application was made and a briefing document was sent to everyone in power, science and the media that mattered at the time, including Dr. Edmund Storms and Dr. George H. Miley, speaking of the application and referencing the work of Matsumoto and Shoulders as people that were close to their invention. That patent was classified later that year. The reason is it relies on magnetohydrodynamics, and that is, per 1980 presidential order, the sigma-1 secret of nuclear fusion. The sigma-1 secret of nuclear fusion is hydrodynamics and nuclear, and that is probably, in my view, why that was classified, because it specifically said magnetohydrodynamics produces nuclear fusion. Conrad says, the positron-electron channel was also observed in many different reactions before. I said one could argue a process that produces detectable E+, E- signatures, right? Like Matsumoto's work in the de-excitation of 4-helium in palladium-deuterium electrolytic cell, which other works cites the de-excitation of 4-helium star in a palladium-deuterium reaction like Matsumoto's did. So I specifically asked him, not just what E+, E- channels occur in other different reactions. I specifically asked him what other authors have claimed that the de-excitation of DD fusion processes leading to 4-helium excited state decays with the aid of a positron and an electron. Okay? I said, since you can't get inside the nucleus or a cluster during a nuclear reaction, both internal pair production, IPC in your terminology, that's internal pair creation, and any other path that produces the observables comes down to a hypothesis on reaction order. Is it the chicken or the egg? Which order did it occur in? Matsumoto's theory is an attempt to explain all of the observables rather than just a limited subset. Just because you do not look for the other observables does not mean they are not there. Your theory suggests there will never be any consumption of palladium or titanium in your metal targets. It's just DD fusing, making 4 helium excited, decaying with an internal conversion of the gamma, converting and producing a positron-electron pair that carries away the fusion energy. There is no room in that. In that reaction, there is zero room for transmutation. Transmutation, banned, not going to happen, never see anything going on in that theory. So, what if this is not true, I posit him? What if the findings of Matsumoto on September the 21st, 1990, in palladium deuterium electrolytic experiment, page 109 to 116 in the book linked for free above, was actually what happens? I predict your targets will, if run for sufficient time, releasing energy, be found to contain new elements in line with those found by all other researchers in the field with successful experiments that run long enough and choose to look at their working material. I predict you will not choose to look at the working material or dismiss things that you may find if you do, because your mechanism will not be able to explain the observables. He then says, as I said previously, in the case of helium-4, this channel is much stronger than the proton channel because of the threshold resonance that was earlier observed. This sounds like a good argument. I then say, for brevity, can you point me to the correct reference so that I may include it in my review of this paper? He says, our study focuses exclusively on the DD reaction in metallic environments. And I replied, this is exclusively what Matsumoto was studying in the papers I sent you. If you want to know really what is going on in metal deuterium systems, you must deeply study your targets before and after the experiment. He then says, we do not intend to explain all the effects you mentioned in your email. However, I believe this is sufficiently ambitious. I said, for one paper, agreed, and it looks good. It does look good. The paper looks good. That's why I want you to get out there and promote it. Let's get those metric numbers up. Let's get a lot of eyes on it. Like Matsumoto, Onion sliced his data and findings from one experiment over many papers. By that token, one cannot dismiss a whole argument based on the contents of one of these slices. So I'm not dismissing everything that they're saying, and he shouldn't either. Okay, I need to understand what they're trying to put across better. They need to communicate it better, because it doesn't look like there's a sufficient amount of analysis, at least in this one paper, to make the conclusions that are suggested in the paper. I may be wrong, but it appears you have not read any of Matsumoto's work, or even the 2 papers I sent you, all in any serious way. Perhaps you have no intention of doing so, which would be a shame. I know from the 200 kilograms of Matsumoto's materials that he read and considered all works published in the field, and I know that all the way up to 2019. What you wrote appears not as a rebuttal based on considering the work, but as a cursory dismissal. And that's exactly what it felt like. The writing by both parties that responded to me looked like a cursory dismissal. But not reading something does not mean it has not been said. Not reading something does not mean you were not informed. I like Dr. Matsumoto's wish on October 2000 for the work of Nardi and Bostic. He says about Nardi and Bostic that if they had looked at their ring traces published in 1980, they would have found carbon in them. Of course, as far as I'm concerned, the argument was a little bit flawed in that specific case, because I think the target material was polycarbonate. Of course, there would be carbon in them. But the idea of Matsumoto's was a good one. I then make an offer. I say to Conrad, I would also like to deeply study your targets and look for not just the presence of carbon found by Solin, Adamenko, Matsumoto, Huang, myself and others, and oxygen found by Iwamura and others, as that is too easy to dismiss for, reasons. But look for the spatial arrangement of those deposits, both within the deposit itself and the intra-deposit arrangement compared to starting material across a number of targets. I think you will not want to do it. And that being the case, if you think you can handle them properly and send them to me, I would be willing to record my analysis of them for free. So, for all of the authors at Szczecin University that published this in Physics Review X, I am saying that you cannot state conclusively what you've said in your paper is how it is working unless you looked at the having looked at the previous before material and then done a long run and then looked at it afterwards in a serious way. I am offering to the authors of this paper to look at those samples. I will record. You can bring the samples to me. You can do the entire chain of custody. You can put them on the analysis tool and you can watch the video recording of the analysis. And if we find nothing, we find nothing on that sample. I would argue that you could do it yourself. I'm sure there are people competent in your field. I know at least Matthew Villat is very competent in doing the characterization under SEM with EDS. I would suggest other tools like SIMS as well to look at isotopes. And then ultimately for analysis with mass spectrometry, ICP-MS. If you find no other reaction products, then great. Then you've got a good case to say that in the specific case that you're arguing, the DD fusion, that there is nothing going on other than that, and that it's more likely in that case that the positron and the electron are coming from internal pair creation, production is what other people call it, and that is doing the de-excitation of the energy. Okay, so that is for the authors of this paper. Now I'm going to actually start going into how the work of Matsumoto, I believe, pioneered this idea to a great degree, and how the signature that's coming out was both assigned to these particles coming out, taking away the reaction energy. Of course, everyone's looking for where the reaction energy is going and where the gammas. It's not an original idea to look at that, but this was pretty early on. He was doing it in literally 1989. And so I think he could be considered a pioneer. And at the very, very least, they could do an addendum to the paper to give credit for Matsumoto suggesting something similar. At the very least. It's the least that could be done. At least, even if they didn't want to look at any of his work, even if they didn't want to study and find out that there was transmutation going on, because their theory doesn't allow for any transmutation. So they better not find any transmutation. It shouldn't happen, right? So don't want to look, but even if you didn't, you have to at least give credit to Matsumoto for suggesting that positrons and electrons coming out of the DD fusion process, whatever there's going on in there, is taking away the reaction energy. Okay? Okay. So, I predict very fully that they will resist, just as some other authors in the field have resisted analysis of their materials because they've claimed there's absolutely no transmutation going on. Transmutation is not a thing, definitely not a thing. Definitely not a thing. Therefore, you can't look at the samples and find out there is. Because it doesn't happen. Okay? Right, so first up, we're going to look at where it does happen. And for those that followed my Flower of Life 2 presentation, I'm just going to give a summary of a couple of slides here. So this was presented on the 14th of September 2025. And you look at these little rosettes, these flowers that come out of the cavitation process, which we know synthesizes elements from Kladoff, from Leclerc, from many authors, including ourselves, and also Royshin and Marza. So cavitation does this. We know that these structures can be destructive to metals and take off a, say, 90 nanometer layer. So yes, they can move materials around in a reactor, and so shouldn't be surprised if things migrate. However, we are looking at a situation where the vortex in these systems is able to rip material out of the metal body and pull it into itself. And that when these structures collapse, they spew out a material, in this case in a tornado vortex, and the material is often larger volume than the structure it's emerging from. Larger volume than the structure emerging from. Okay, this is one that just broke up, and you've got a little series of levels here, and I would see these as sort of coherent matter waves. These are centripetal de Broglie waves, and they're resonant wavelet radii from the core, and it inflates as the confinement fails. This is where, in my view, the overall outside came out. So what do we see in these things? Well, the substrate is basically copper or copper and oxygen. But when we look at these things, we see in a cavitation process all of these elements: magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, iron. Copper was also already in the original material. And we will have some nitrogen and oxygen in the water and in the dissolved gases. And here we see carbon and potassium, chlorine and sulfur. Here we've got the same kind of elements going on. Here we've got the same kind of elements going on. Here we've got the same kind of elements going on. Here again, in all of these different cases. In this case, in this particular one, we've also got a signature of fluorine. Okay. So this is what we've seen in Bingwen Huang's reactor from cavitation process, from the magnetohydrodynamic structure that did the work there. In this experiment, which was using doing explosive cold fusion in palladium and deuterium, okay, the elements in the experiment were deuterium oxide, was the heavy water used. He had sodium chloride as the electrode. He had the electrode for which the fusion was supposed to be occurring in was palladium, and platinum as the counter electrode. Okay, so they are the elements. Now, just like Stephen E. Jones was trying to explain in his 35 day after Pons and Fleischmann released their report publicly, he was trying to, in his paper published in Nature, he was trying to explain 3-helium that came out of the ground. 3-helium is the decay product of tritium, okay? And tritium and 3-helium are the fusion, main 2 fusion branches, which I will show you in fusion of deuterium and deuterium. So you have 2 deuterons here, they fuse. One branch gives you tritium and a proton, and the other one gives you 3-helium and a neutron. They should happen 50-50 split. So he observed tritium, 3-helium, and fluorine. There's the fluorine. Neon, very interestingly, and also he observed in EDS, so this separates that out from tritium oxide, okay, or the not OH but OT. You separate out the fluorine here because you also see it in the EDS. So fluorine, magnesium, aluminium, silicon, phosphorus, sulfur, potassium, calcium, titanium, iron, copper, zinc. Pretty much everything we see here. Okay, pretty much everything we see here. Now, in Ficcardi's 1994, I actually held this reactor, this core in my hand very graciously. and very lucky to have done that in December 2014. In a study of this sample from 1994 and 2000, which was nickel hydrogen. So this is palladium deuterium, this is nickel hydrogen. These are cold fusion 101. He found, or rather they found, Ficcardi and Piantelli, they found fluorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, chromium, magnesium, iron, copper and zinc. Very, very similar to what we're seeing here, and almost all of the elements we're seeing here. Okay? All right. In addition, they found a ball with the transmuted material behind it. The ball with material affected behind it. This is a close-up of it. Very similar to our ball lightning tracks, very similar to Matsumoto's deposits, which we produced with the ball with the stuff behind it, ball with the stuff behind it, ball with the things coming out. And in Nestorovich's report on the work of Moscow Nuclear Physics Institute of Bogdanovich, they observed and based it on a topological monopole that was produced by a pinch electromagnetic vortex. They are saying that they produce iron-rich crenellated spheres, which has a hole at one end, which is in the azimuth of the direction, only on one side. Okay? Substantial evidence in support of this hypothesis may be provided by spherical objects with a hole on the axis, found in significant numbers in the post-discharge period on surface covered with tracks. In the case of Matsumoto, in 1998, this happened. Out of the hole on one side, where the magnetohydrodynamic structure fails, the material that's inside comes out. Okay, so there we have it. But I hear them saying, yes, that is standard cold fusion 101, palladium and deuterium. It's standard cold fusion 101, nickel and hydrogen. But, Bob, we were using titanium and deuterium. We were using titanium and deuterium. Yeah, it's not showing transmutation either way in titanium to deuterium. Well, for that, we can go to Leonid Oretskev and his work. And it was at the Kurchatov Institute. These are basically the experts in ball lightning. And here we are. Okay, so this is Leonid Oretskev, a mainstream physicist, okay? A mainstream physicist at the Kurchatov Institute, saw the anomalies at Chernobyl, could not explain them with any mainstream physics, and wanted to have an explanation, and so he came to the field of cold fusion. Okay? And we will look at this now. So what did he do? He put some titanium wire in water, and he put a high intensity discharge through it. It was in a container, and out of the top, he had some pulses here, and out of the top he filmed it, and he had a mirror looking over the top, had a high frequency frame camera there, so he could see both from straight on and from the top. And these are 1 millisecond apart. They saw a ball lightning form on the top, which they can see from the side and from the top. Okay, and the ball lightning became more clear, and then the ball lightning decayed in 6 milliseconds later into loads of micro ball lightning. Loads of micro ball lightning. Okay, and these micro ball lightning, in my view, are on the boundary. And if I go to it now, give me a second. They account that what happens is, I believe they're made in the core, and then they spray out and they go around on the boundary, and because of their toroidal moments and such, they self-organize into a mesh on the outside of the non-radiating boundary of the macro ball lightning. But because they're smaller, they can survive longer, so they then re-emerge a few milliseconds later. So if you look at this, the exposure time was 130 microseconds, and each delay between frames was 1 millisecond, and there are 1, 2, 3, 4, 5. So this is actually 5 milliseconds later to the breakup of the outside of the ball lightning. and the microball lightnings going everywhere. Now, we saw microball lightnings fusing oxygen on copper oxide to sulfur on the snowballs on cobblestones. But I think the more interesting data point, which is relevant to this, is what we observed in the Vega experiment. And for those that don't know, it's called, let me think about it, it's a 15 millimeter ball lightning cut. And I almost only need to show you the cover frame here. But essentially, if I pull this up and go full screen, this is what we saw here. And these were scallop sections on the boundary. So we're looking here at a ball lightning cut in a copper pipe here. It was a hemispherical cut, okay? Amazingly, this very sharp point here is absurd given the fact that copper is the second or one of the most thermally conductive metals there is. And you can see 15 millimeters here. It's roughly 10 to 15 millimeters, this cut. And so on the boundary, this area here where I'm looking with this little blue cross here, you can see it here. If I wave my mouse and it gets really big, I'm talking about that there. Okay, for those people that can't see mice. So I look here, you can see this is the boundary layer. And it's not melted and it's a big smooth blob. It's loads of scallop sections and with different orientations of a churned section of nanometric structures, which we go in and we look up really super duper close. Okay, so you can see that this scale down here is 1 micron. So the distance from this side to this side is 1 micron. Okay, 1 micron. Sorry, 3 microns, about 3 microns, which means that these are nanometric. Okay, these are all about, I would say, 250 nanometers across. Now this is pointing into the camera, into the viewer. This is pointing into the viewer, this one in the center here, right? This one over here is pointing up in this direction. This one is pointing in a different direction. This one is pointing in a different direction. This one's pointing in a different direction. This one's pointing in this direction, okay? So I would argue that these are the microball lightning that are on the outside of the large ball lightning. I've said this many times, okay? All right. So what he found in this experiment is that the composition of the titanium was almost, well, it's 99 point. We wouldn't call this 3 nines. It wouldn't even, it's basically 2 nines. It's pretty pure. And there's very small fractions of other elements here. But when they look at the material, firstly, the titanium, the 48 comes down. So after the experiment, it was much lower and the natural ratio is up here. So titanium 48, the most abundant isotope of titanium, is reduced in abundance, and the heavier and the lighter isotopes are all more than natural abundance. So it's produced both lighter isotopes of titanium and heavier isotopes than titanium. But more interestingly, looking at the analysis, what they see is titanium fits in here. It's between vanadium and chromium, or before there. Anyway, it's one of the two. And so you take titanium out of there, but you're getting sodium, magnesium, aluminium, silicon, potassium, calcium, vanadium, chromium, iron, nickel, copper, and zinc. So these are both heavier elements and lighter elements than the titanium. So not only are you getting heavier and lighter isotopes of titanium, you're getting heavier and lighter than isotopes. So what that says is that in exploding titanium foil, you're getting synthesis of heavier and lighter elements. In the case of cavitation of copper in light water, you're getting like a wide range of elements which are not in the starting material, born out of these structures. In the case, and in this work of Leonid Roitzkiev, they actually see in the spectra of the ball lightning, they see a range of different elements in there. And they go into it at some point. I can't remember where. Okay. Also in this paper, they see the monopole, the monopole-like structures and the plasmoid-like structures and so forth. There's a second paper which discusses this, and they've got color diagrams in this one, which is all very nice, and they talk about the titanium isotope and how it, in this case, it goes from I think this is by mass or something, I don't know, but it's 73 point something percent all the way down to 68, and then all of these they have more of the non-natural isotope ratio is changed. Again, it's repeating the graphs from the previous presentation, okay, and they go into an explanation of how this might be occurring, and they show these images again, and they talk about the tracks. Okay, so, and you're not looking at that, but anyway, I was showing this paper. It's just another one of Leonid Oritskyev's. Okay, okay. So, what I've shown you is palladium deuterium cold fusion 101 produces a range of elements. Nickel hydrogen cold fusion 101 produces a range of elements. Titanium hydrogen source produces a range of elements. Why would you say that a reaction is only going to produce a fusion to a helium and then produce, how should we put this, this positron-electron pair? That there's no means in that story for other transmutation to occur. So, the problem is for this group is for it to be credible, even just a little bit, they have to categorically prove there's no foreign elements or foreign isotope ratios in their finishing material compared to their starting material. Okay, that's one thing. Okay, and then let's look at the key parts of the data. All right. So, first up, this is the brainchild of Konrad Chersky, right? He led the research group for this part of the European-funded project. This is Konrad Chersky, University of Szczecin, okay? 140 publications, 2,009 citations, very, very respectable. Okay. So this is the paper. It was published in the very, very respectable journal Physics Review C. And in here, he basically posits that through a whole bunch of nuclear equations and resonances and electron screening equations and so on, that there might be this path. Okay. So this was published in 2022. And so he is looking for an experiment to show that this might be present. Okay. This is the experiment in question. Now, I actually really like the way the first couple of sentences are placed in this. It's saying here, I'll zoom in, experimental signatures of a new channel. It's not saying experimental proof of a new channel. It's saying experimental signatures. This is the right way to phrase it. I like this. It's conservative, of the deuteron-deuteron reaction at very low energy. Okay? So, full respect for calling it experimental signatures, not experimental proof. Then I'm going to read the first line. This is often the most people will read. The discovery of a new positron-electron reaction channel in deuteron-deuteron fusion at very low energies. There we go. If we read the first line, which most people will do in isolation, we will believe that there has been a discovery of a new, like never been said before, reaction channel, which arguably is, if it's a gamma-induced internal conversion to a pair positron-electron pair production, then it would be. That's honest, that's true. And they're saying they've discovered it. Okay? And then they add the word might on the second line. So, is the might some sort of proviso in the way that signatures is a proviso? Or is it we've made the discovery, and if this discovery is applied, it might have major implications for understanding primordial and stellar nuclear synthesis. Okay, right, well, maybe, don't know. They go on to say determination of the branching ratios between emitted protons, neutrons, and positron-electron pairs for deuteron energies down to 5 keV. Okay, well, you can go and read this paper in your own time. Essentially, Mathieu Vallat prepares, as far as I understand it, Mathieu prepared these targets in an old Celani cell. It's just, you could easily put the material in there and you could pressurize it with deuterium and heat it up if necessary. I don't know, at least when we went to visit Szczecin at ICCF 25, that's what he said was being done, and he had a cell there in any way. Maybe, maybe not, but it would be nice to think so, that something out of the early MFMP's work played a role in this. Anyway, so I guess this might be some sort of co-limiter or guider. I think this is a means by which to guide the deuterium beam to a spot target. The zirconium, oh, it's not titanium. This one's zirconium. Was it always zirconium? Have I got it wrong? Yes, this is zirconium. So they use zirconium. So forget what I said about titanium, but it's a metal, so there we go. So my apologies, I was talking about titanium, and it wasn't titanium, it was zirconium. My bad, I'm wrong, bye-bye. Anyway, zirconium, that's the deuterated zirconium, it's there, and they're firing more deuterons in it. Thank you very much, John. Thank you very much. Experimental signatures for donation. Actually, that looks like a real donation, John. Thank you very much. And then they fired it through, there was particles coming off, and they put a screening foil, I guess of various thicknesses, in front to take out other energies, and it hit into the silicon detector. Okay, ultra high vacuum. So here's it in a more 3D view. So the deuteron beam is coming in here, and we actually saw this device in their lab, and it was very, very shiny. And so, you know, where the 5 million went, in at least part of it, 5, 6 million, whatever it was. And the deuteron beam is coming in, it's hitting the zirconium deuteride target, and it is firing out the particles. And then this is the aluminium foil silicon detector. So there we go. They've also got a sodium iodide detector or a germanium-based detector here for looking at the particles. Okay, so that is the basis. And essentially, they see the protons here, which would be coming from the 2 deuterons to tritium plus proton channel. They see the tritons here, which will be the tritium, which you will see, and the helium-3 will be the helium-3 plus neutron channel reaction. Okay, energy spectrum measured with a silicon detector, blah, 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 blah. Because the very small thickness of the detector, no electron or positron bump could be observed. Okay, so they don't see that. Okay. Then here they are looking at the gamma spectrum here, and they're seeing energies up to this energy, and this might be to do with the beam here. So this is the experimental spectrum, 10 keV, background spectrum here. Okay. The money shot really is two money shots. One is the Bremsstrahlung radiation because of the de-excitation. So what they're saying is these electron-positron pairs have an energy. The energy will be shared between them, and so you will get a spread spectrum up to somewhere over 22 MeV. And so you're seeing the Bremsstrahlung there. This is where I think it's interesting. They're talking about the enhanced branching ratios here. Now, it's actually easier to go to steps to the discovery of electronuclear collapse and look at Matsumoto's earlier work to find the branching ratios. And essentially, it's equations 1 and 2 in his book. It's always good to have it as 1 and 2, not those. That's 4 and 5 and 6. Here's your normal reactions that you get from DD fusion. Okay? Deuteron goes to 3 helium plus a neutron, or a triton plus a proton, or 4 helium plus a gamma ray. And this is the problem with cold fusion from the beginning. is that they don't see the neutrons or the tritium. They do see helium, but they don't see the gamma. So how are you seeing that? Because effectively, here are the reactions, and reaction 1, this one, and this one take place with approximately equal probability, and they're about 50-50 between these two. And equation 3 is about 10 to the power 7, 7 orders of magnitude less than these other two. It's so insignificant. So how do we get a lot of 4 helium forming and no gamma? Of course, some people have argued, like even recently, it could be from spallation, or you could call it cluster decay. That is, the 4 helium is just falling off the palladium, just coming off, right? Or it's some other reaction going on. You see, if you had 4 helium coming off, it's like kind of knocked off or sucked off, then it wouldn't have that gamma ray. But anyway, then you would have some transmutation going on. But we're not seeing transmutation, or we're not looking for transmutation, so we're not seeing it. Okay. So they have these branching ratios, and they're saying that with this process, by using 10 and 20 keV deuteron beam energies, they're getting different branching ratios, and that as it gets down low to the resonance, which is enabled by the electron screening partially, that they are seeing much higher branch ratios. So I think this is saying under the internal pair creation silicon detector, they are seeing 0.42 of the overall branches in this. So that would be around about 0.5%, less than 0.5%. But if you do 20 keV, you're getting 0.06 of 1%. So not a lot. And that the ratio between this one and this one is 7 times. So by lowering the energy to 10 keV, you get much, much higher reactions, okay, in this particular branch. Now, these are for different detectors. So this is a silicon diode or something like that, sodium iodide. This is for annihilation radiation here, annihilation radiation. And they're saying 1.7 to 0.16. This is 10 plus or minus 3. And then this is 1.1 over, this is 9 plus or minus 3. Now, the question I have is, they have this theory on the end here. Now, I don't know whether this is Conrad's theory, but what I will notice that the theory predicts 0.25 here. And this is nearly, oh God, it's at least sort of 80% or 70% larger than that. This is double or more. This is nearly triple. This is a lot more than triple. This is, this is more like 5, 6 and a bit times more. This is over 4 times more than the theory predicts. And then in this case, it's 50% more here. It's more than double here. It's more than 4 times, 400% more, or 300% more than this. And this is 200% more than this. All right, this is 3 times that. But the ratio is better. This is 5.8 and this is 9, 10, 9, 7. And if you do the lowest bound on this, the lowest bound on this, the lowest bound on this, and the lowest bound on this, you almost get to this ratio. And it's kind of hiding the fact that all of these are quite far out. So what I'm asking here is, what is the plus and minus on the theory? Because they give a plus and minus here, plus and minus here, plus and minus here, plus and minus here, but they don't give a plus and minus on the theory. Is the theory an absolute thing? So what? I don't know. But is this pretending it's agreeing with theory based on a ratio at the lower bounds of these, bounding errors? I don't know. And this is why it would have been really nice for them to have started a conversation. I would have loved to have been on a proper Zoom call with them and gone through the paper and asked them X, Y, and Z. I don't think anyone else in the world cares enough. Honestly, sorry to the authors, I just don't think anyone cares enough. There might be someone that's in future doing electron screening, and they are wanting to have a reference to reference, and they'll reference this because it's a paper on electron screening. But I think there's few people in the world that would care enough to me to actually work through this whole paper and try and understand where they're coming from. I would like to have had a conversation. I gave them 5 days to have a conversation. I immediately reached out to them. I asked them many questions. They did not answer a single question. I gave them things to read. They did not read a single bit of it. They showed no evidence of reading it. No evidence of reading it whatsoever. So I'm reading their thing as best I can, which they've taken, you know, nearly 6 million euros to build, right? And tens, if not 100 man years to produce as total effort. And they won't even answer simple questions or read something or engage in any way apart from dismissive, cursory emails. Well, okay, all right. Well, this is, though, where the data is really strong, in my view, for a positron-electron annihilation. And what they're saying here is in B, when they have the 10 keV deuteron beam, compared to background, they say this huge 511 keV annihilation peak. Huge 511. Look, this is a logarithmic scale. This goes from 100 to 1,000. This is 2,000, and this will be again. It's the next logarithmic step, so you can see how they go. So this is probably where is it? 2,300, 2,400, whatever. Okay. So this is very much higher than the background. Okay, so this is very good for proving that there are positrons and electrons annihilating. Okay, which means somewhere there must be some positrons. Okay, in the present work, we theoretically explain our electron observation by considering the existence of DD threshold resonance in the 4 helium nucleus and its internal decay. Sorry, its decay via internal E plus E minus pair creation or pair production. Okay. Okay, so they do the maths, they come up with an equation, and so this is essentially what they're saying is these are the branching ratios which I was showing you before, or the branches that are possible. Where is that going to actually? I don't want any of that. I hate the new AI features. Stop it. Stop it, just, oh, there we go. Come on. Come on, and just let go. All right, fine. Deuteron plus deuteron goes to triton plus proton. Deuteron goes to 3 helium plus neutron, or deuterium goes to 4 helium. But rather than this is representing an excited 4 helium, which has the 23.84 MeV that's released by these things compressing to this. It's releasing that excitement here by a positron and an electron emission. And these are coming down to here. Now, the implication here is that the positron is going off at an angle and the electron is going off at an angle. Okay? Now, this means they're not coming off together. And then the positron hits an electron and causes an annihilation somewhere else. And so some people have said, oh, you can prove this by doing you have two scintillators like sodium iodide, 180 degrees apart. Thank you very much, Skoggy Hoggins. That's really, really very much appreciated, that £50, really. You have 2 scintillators. The positron annihilation with electron occurs in the middle, and it sends off 2 photons at 511 keV, one way and one the other way. Well, if you did do that, all it would do is just prove that you've produced a positron. It wouldn't prove that something, was necessarily structured in a different way, because he's saying that the energy comes out here. So basically the positron-electron internal pair creation, internal pair production, takes away the excitation energy and returns the particle to ground state. Okay, So that's it. And now here it gets a little bit more bold. It says, thus we found clear indications of a new positron-electron channel in DD fusion via the formation of 4 helium threshold resonance and its decay to the ground state as schematic represented in figure 9. And this changes the branching ratio for these outputs. Now I want to show what Matsumoto showed. Essentially, I described earlier what an iton is here. It says the new particle itons. The NATO model predicts the production of a new particle itons. It's actually it's a composite particle. He would have helped himself by putting a composite in there. During the hydrogen catalyzed fusion reactions, the itons are considered to consist of electrons, positrons, and neutrinos. This is his last sort of document on the work, not his early work. Okay. While the iton passes through the material, the electrons of the iton are torn off. So basically, since more electrons than positrons are involved, the itons are negatively charged. Okay? When the itons are produced during the compression process of the hydrogen cluster, they are emitted to cover up the nuclei of the product particles. There's a breakup of itonic particles inside the quad neutron underwent gravity decay. When the iton passes through the material, the electrons of the iton are torn off by deionization. So he's saying that the iton, it can be at least an electron-positron pair. Preferentially, they should be bound with this neutrino that comes out from the polarization of the proton, okay, leaving a neutron. And then that collects other electrons into a macro cluster, and that it's overall negative charged. But as the thing comes out and leaves the overall reaction area, the other electrons are ripped off, okay? And then it just leaves the last electron and positron bound together with the neutrino, and then these decay. The sequential breakup of the network of itonic meshes was successfully observed on nuclear emulsions shown in figure 4, reference 20. Okay, so we'll look at those in a little while. Okay. And of course, he doesn't have just one reaction. He has a lot of reactions, and on page 46 you can see these. So, you know, he explains how each of the different things that you see in this whole reaction chain occurs by different things occurring. Now, if you only say you are going to look at two deuteriums fusing, and all that's coming out of that is this positron and electron, and that is what we've observed, and therefore that is the story, and that explains the branching ratios. That, in my opinion, is not showing the whole picture. The whole picture in all of these type of systems is a lot more interesting. Okay. So, so he goes into more detail here. The first is the itonic particles. The NATO model introduced new particles to explain the strong compression of hydrogen clusters as well as aneutronic reactions during cold fusion. Then 2 candidate particles were proposed. Itons were complex particles consisting of electrons, positrons, and neutrinos, and just interconnected electrons. Some traces suggest the decay of the former particles were found on nuclear emulsions, although the number of traces were less than expected, 40. As a result, by latest underwater spark discharge experiments, it was made clear that most of the itonic particles were interconnected electrons. Okay? However, as predicted in the paper, the following conclusions were not so changed. At this point, he's kind of basically saying, yeah, I kind of expected more of these positron, electron, neutrino particles, but basically most of them were electrons that were bound together. And I think this is why he warmed to Ken Shoulder's ideas. And then he talks about the chain reactions. Anyway, so why is he trying to explain various phenomena? So if we look at his first paper on the subject, received August the 14th, 1989. So we're like 6 months away from Pons and Fleischmann. He's saying, these are the principal reactions you should normally get. D plus D goes to tritium plus proton. D plus D goes to 3 helium plus a neutron. The fusion reactions rate respond to 10 to the 11 to 10 to the 14 fusions a second. On the other hand, the fusion reaction rate of 10 to the 4 fusions was obtained from data of neutron and tritium production, which are considered to be direct productions of reaction. Okay, Jones, that is Stephen E. Jones, credited here, this is one of Jones's citations, believed that they succeeded in measuring the 2.45 MeV neutrons emitted from the reaction. However, the heat production rate that is calculated from the neutron emission data is extremely small compared with the data from Fleischmann and Pons. Okay, so there's a series of questions here, and in his response, he does this. On the other hand, in the case of cold fusion in metal, deuterons are compressed to an extremely high pressure in and or on the surface of the metal, so that no fewer than three, this is very specific to his theory, you need a minimum of 3 deuterons can gather to form a cluster. For example, in the lattice defect, so it can be on the surface, a lattice defect, or in a crystal grain boundary. In the cluster, electrons move around following the deuterons with heavy mass, so that the effective mass of the electrons becomes fairly large. Now, the effective mass of the electron is what drives muon catalyzed fusion, because a muon is 207 times the mass of an ordinary electron, so then it orbits closer to the nucleus, its centripetal de Broglie wave, its matter wave, orbits closer to the nucleus, and when you get a deuteron that has an electron replaced with a muon, combines with a normal atomic deuteron, then they're so close together that the strong force takes over and they merge and they produce 4 helium. Okay, that's the theory, or you get fusion events occurring, and that is muon catalyzed fusion. What Jones was saying in his 1989 paper, 35 days after Pons and Fleischmann, was that there was some quasi-particle. He's not saying what the made-up particle is. He's not saying where it's an aggregate of particles. He's saying there's some actor, he's calling it a quasi-particle, that plays a similar role to a muon, but so effectively it's a heavier mass electron-like process that then allows those things to come together in geological processes to explain the 3 helium, which is a decay product of 3 tritium and or a fusion product that comes out of geological processes as observed. But what Matsumoto is saying here is we have noted the reaction occurs with the largest probability and predominantly contributes to heat production. And this is, basically, in the cluster, electrons move around following the deuterons with heavy mass, so the effective mass of the electrons becomes fairly large. The distances between the deuteron nuclei in the cluster are sufficiently short to make fusion reactions possible. 2D plus D goes to 4 helium. This is an excited state plus a deuteron. The recoil energy is transferred to the 3rd deuteron, this one here, and or to the deuteron cluster. Okay? Reaction 3, this one here, which we have not observed, is impossible in the gas or plasma state. Okay, not possible in the gas or plasma state because it is essential that the 3rd deuteron that receives the recoil energy exists very near to reacting deuterons. Reactions 1 and 2, which are ordinary DD fusion reactions, do not occur because the energy of the colliding nuclei is too low to strip a neutron or proton from the deuteron nucleus. So he's explaining why there's this vastly changed ratio back in his 1989 paper. It then goes on, there's many body fusion reactions that are possible where you can get lithium formed, beryllium formed, and boron formed. And he says that basically from Fleischmann and Pons, the gamma ray spectrum using sodium iodide scintillator shown in figure 1a reference 1, they explained that the spectrum corresponds to gamma ray emitted by following hydrogen reaction in water. Okay, so, but he says the intensity of this gamma ray is so weak that the assignment is doubtful. So Matsumoto is calling into doubt the work of Pons and Fleischmann. He's saying the author considered that the spectrum is due to the gamma ray emitted from fusion productions in reaction 5. So reaction 5 would be this. The lithium is actually coming from here. Okay? So the lithium isn't from the electrite because Pons and Fleischmann were known to use that. It's actually coming from the reaction of 3 deuterons going to 6 lithium. Okay, excited state and then decaying with a gamma. Okay, So he's saying that you're seeing these various gamma coming out of here, and this explains in this chart why the distribution is here. And he's just showing that this is 8 beryllium, this is the lithium, and this is the boron. Okay. The NATO model also predicts the fusion products. The production rate of 4 helium is greatest in the predominant reaction 3, since reactions 1 and 2 are not direct processes. The quantities of tritium, 3 helium, and hydrogen are much less, similar to neutrons. Furthermore, it can be predicted that many body fusion products such as 6 lithium, 7 lithium, and 8 beryllium are produced, but also in fewer quantities. If the extremely high concentrations of deuterons are obtained, 12 carbon, 14 nitrogen, and 16 oxygen can be produced by single reaction of many body fusions. Those isotopes are stable and important constituents of the Earth. The NATO model suggests some modifications to the theory for the birth of the Earth, as well as the feasibility of production of useful elements such as rare earth elements, metals rather. So he's saying all the way in his first paper in American Nuclear Science here, that he's got in his book, that was received August the 14th, 1989, that you can get the production of carbon, nitrogen, and oxygen in these processes, including the lithium and beryllium there, and it's because of many body fusions. Not even a thing considered, and not allowed to be considered in the paper that we discussed earlier. Okay, now going on, in this second paper here that he refers to in his book, received November the 13th, 1989, he talks about this. High energy particles such as positrons, deuterons, and protons are emitted. These particles make surrounding atoms in the sample excited or ionized, which results in X-rays being radiated. Moreover, the positrons annihilate with electrons to emit gamma rays 0.511 MeV per gamma. Okay, so he's talking about this reaction in hydrogen in this case. 2 hydrogens plus a hydrogen goes to 2 helium plus a proton. Okay, so he's saying that you get gamma right here, like this is the second paper in his book. Okay, the second paper in his book. This is the first reaction we talked about, but then he talks about in light water. Okay, now he goes back to heavy water. He sees these various spectrums here. There is the positron and electron annihilation peak here. Okay, and so forth. Okay, says for heavy water, on the other hand, it is predicted that a new particle iton will be emitted in reaction 1, which I showed you earlier, with 20 mega electron volts of energy. So he's already saying here in November the 13th, 1989, November the 13th, 1989, that in deuteron fusion, a iton, which he's already specified includes a positron and an electron, is emitted, and that is emitted with approximately 20 mega electron volts of energy. That is the energy of excitation. The iton that is introduced in reference 4 takes long-range interactions between nuclei and can be emitted from the hydrogen-catalyzed fusion reaction if the excess energy is sufficiently large. Okay, so he then goes into more detail on the next one. March 26th, 1990, it was submitted. In here, he says, when the NATO is formed, electrons connecting hydrogens are also pressed extremely close to the hydrogen nuclei. In the hydrogen nucleus, the depolarization takes place by inverse beta decay. So a proton is polarized, depolarized, and gets neutron and positron and a neutrino. Neutron, positron, and a neutrino. A dipole there consisting of an electron and a positron is formed, receiving the quantized excitation energy of the fusion's nucleus. The iton is emitted as. So he's saying that the electron and the positron receives the quantized excitation of the fusion nucleus. Now, in Konrad Tversky's speech, they would say that this is formed, and the quantized excitation energy is the 23.8 whatever mega electron volts. It's 23.85 mega electron volts of photonic energy. But if it never becomes a photon, is it ever really a photon? Is it a virtual photon? What even is a virtual photon? What he's saying here is the excitation energy, whatever that is, whatever you think it is, inside that nucleus, that 4 helium excited nucleus, leads to a dipole there which consists of an electron and positron. This is right here, effectively internal pair production, or as Konrad Tversky calls it, internal pair creation. Okay, so it receives that quantized excitation energy of the fusion nucleus, and the iton is emitted as the electron and the positron plus the neutrino here goes to an iton, and it's this kind of structure. It is assumed that a neutrino is also contained in the iton. He's not saying it absolutely is contained in the iton. He's just saying it's assumed. But very least, a positron and electron is created from the excitation energy and released. He's assuming that the neutron doesn't go out because it's all happening simultaneously. All of this is happening simultaneously. And the neutrino is also contained in the iton because no gamma rays are observed due to the annihilation of the electron and positron pair. So initially, you don't get the electron-positron pair. Now, if you did see the electron and positron pair annihilation, what that would mean is that possibly the neutrino isn't part of the iton, and that the iton is only the thing that carries away the energy is the positron and electron pair. This is why I am saying Takaaki Matsumoto should be credited for positing this de-excitation method. He's very precisely saying that I haven't seen this particular large scale of positron-electron annihilation. Therefore, if that's not the case, then these must be bound, and the neutrino is binding them somehow, and they're emitted as a quasi-particle. Okay? If, for some reason, in the future, someone finds the positron and electron annihilation peaks, then maybe there is they're not bound when they're emitted. Okay? And then you can remove my assumption. But he is specifically saying that the excitation energy from the DD fusion is creating the positron and electron, and that those are carrying away that energy. Okay? All right. The other thing is, if you do have a neutrino involved, then there could be some of the energy carried away in the neutrino, but if they're all in the package together, all of the energy is sort of going away with that, with some recoil from the fusion products. Of course, this particle is unstable, so that it decays in the inverse direction of equation 2. So if this particle is released, then it decays in this reverse direction, so it will produce a neutrino, a positron, and an electron. And if this is the case, and it does produce a neutrino, then neutrinos are coming out of a cold fusion reaction and could account for some interactions that cause beta minus decays. Okay, just saying. Okay. Or beta processes. And then he goes on to, if there's 2 electrons are pressed into focus on the nucleus, you get a double iton, an I2, and so on. And these are kind of things that can go on. Okay. He says here, it can be seen that the electron and positron pairs are emitted almost perpendicular to the transverse directions of the itons. And this apparently is in figure 3. And what he does is he looks at a load of emulsions, and the new book has much better quality images. But I don't actually know on this particular slide which one he's referring to the iton here. But some particle comes in and it goes into and out of the page. and it produces these kind of patterns from the iton collapse. So this was the basics, and one is coming out of and into, and so this was the decay, and they decay and go in either directions, okay, when the iton decays. And what he finds is that when you have a track produced, these are the angles between the itons, and you can see that a good proportion are tending to 90 degrees this way and 90 degrees that way. That's how I read it. But on a control sample, a control material, there's no particular order that you can see. So he's saying essentially, and he does it down here as well. This is the background. There's basically no real order there, but there's definitely a well here. He's definitely saying that these things are coming across the surface, and then they blow up and they go in opposite directions, or basically look like they're going in opposite directions. Okay, and that's why he's saying that something, a quasi-particle in the terms of the 1989 paper by Stephen E. Jones, there's a quasi-particle, and that is able to interact with the emulsion, and then that breaks up and goes off in opposite directions. Okay. Now, in February 26, 1990, he submits another paper here, and he quotes this same reaction here. 2 deuterons plus a D go to 4 helium plus a D. Okay? And he shows potential reaction energy ratios, calculated kinetic energy for hydrogen catalyzed fusion reactions. So he's working out these kinetic energies. He does this mathematical equation. He predicts some particle energies that are coming out here. This is the experiment with the palladium foil, the deuterium oxide solution. Then he has the emitted particle here, and going to a solid state detector, you know, the same kind of thing that was used in the Physics Review X paper by by our colleagues Rakesh Dubey, Chersky et al. And Matthew Vilat. And he says here that he does equations and does some calculations. So you have calculated energies, so comparison of experiment and calculations for cold fusion products. Experiment reference 5. Total calculated distribution based on the NATO model is B here. I think this is A, this is B. C is total calculated distribution based on conventional fusion reactions here, which is different. Partial distribution with 4.7 MeV, and then partial distribution with this, and then that. So, okay, so he does some equations, he looks at the originals, and then he compares with the theoretical model, and then he comes up with the prediction of a new particle, and he says here, however, some questions remain that should be answered. The first is the difference in Q values involved. The modified Q values of 4.77, 3.76 and 2.77 MeV gave good agreement between the calculation and experiment, i.e. he calculated what these things should be, and it turns out that the values that are observed are very good in agreement with what was calculated based on the model. Okay? While the intrinsic value is 23.85 MeV, we have to explain where this difference of approximately 20 MeV in the Q energy goes. The second is the branching ratio in the two-body fusion reaction. In the conventional reactions of equation 1s, the ones that I say go to produce protons and neutrons, production branches are almost equally probable, that's 50-50, and extremely large for the one with 4 helium and gamma. That is to say, this is 7 orders of magnitude less than the other two. Furthermore, in the muon catalyzed fusion reaction, the conventional reactions are predominant, as observed in high temperature plasma. As the NATO model a priori assumes 4 helium production without gamma emission, the reason is that the 4 helium production branch exceeds those ones for neutron, proton or gamma production. And this must be explained. The third is the size of the NATO, which was not discussed earlier, the way they form the NATO, and so blah, blah, blah. To answer these remaining questions, we will now add a new hypothesis, keeping within the framework of the NATO model. Let us assume that one or more light particles are emitted during the hydrogen-catalyzed fusion. This particle can then take away the difference energy of 20 MeV. We temporarily call it an iton, which means string connected with an atto. Okay? If the iton is a meson, it can be neither pi or k meson because the rest mass of these is 135 and 494 MeV respectively. Other mesons must have much higher, heavier masses. Thus, the iton could be a new and unknown particle. Another possibility is that the iton could be a neutrino or electron-positron pair. Neutrino or electron-positron pair. Okay? The itons should remarkably affect the branching ratio of two-body fusion reactions. He's saying that the first reaction is the 4-helium excited reaction, not the proton or neutron paths. Figure 3 shows the energy level of the excited 4-helium nuclei produced from the deuterium-deuterium fusion. Due to the two-body fusion reaction, 4-helium excited is formed, excited by the 23.85 MeV. In the conventional reactions of equation 1, 4-helium opens up the channels to neutron or proton production, and the difference in energies of 3.25 and 4.05 MeVs are transferred the kinetic energy of the particles. In the hydrogen catalyzed fusion reaction, however, quantized energy of 22.1, 20.1 and 19.1 MeV would be transferred to the emission of one or more itons, which might be, possibly, an electron-positron pair. The remaining would be distributed among the kinetic energy. So the remaining difference energies, 3.75, 2.75 and 1.75 MeVs, would be distributed among the kinetic energies of the emitted 4-helium and the deuterons. This is how the hydrogen catalyzed fusion reaction can occur without the production of neutrons, protons or gamma particles. Right. He then explains why it might need to have it be a new meson, because it should involve the strong nuclear interaction. Okay, he thinks it should be. And here is the graph. This is the money shot. Okay, so your deuterium and deuterium fusion produces 23.85. There is a balance of energy that gets shifted out by the deuteron or 4-helium that is produced in the fusion reaction products. And then because you've got a minimum of 3 deuterons playing a role, and then the bulk of the reaction energy is emitted as itons at various levels of energies, okay, depending on which product you're looking for, okay. But because of the way it works, most of the reaction products is going to be deuterium-deuterium to 4-helium. Now, he's showing how this works, essentially in a semi-classical way. This is so anyone can understand this. Let us consider a situation in which a molecule A and B deuterons exist. So A and B deuterons. They're in a highly pressured space, a hole, that's such as a grain boundary of a polycrystalline metal. Now a third deuteron, C, this one here, is assumed to enter the space. This could be, for instance, I don't know, by firing a beam of deuterons at the metal that's got a ratio of metal to 2 deuterons per metal atom. Okay, you're firing a bunch of individual deuterium ions into a metal that has metal 2 deuterium ions. So titanium deuteride or zirconium deuteride would be candidates. Now, the third deuterium C is assumed to enter the space. As a result, the pressure increases to a value that is higher than critical. The electron combining the A and B deuterons is pressed by the invasion of the C deuteron, so that the effective mass of the electron increases. So, as this comes in, it compresses these, and so the electrons effectively are compressed, so the effective mass increases, and so all of these nuclei get closer together. Okay, shortening the distance between the A and B deuterons, shortening their distance. Unlike the muon catalyzed fusion reaction, a symmetry exists in the hydrogen catalyzed fusion. So there's a kind of a three-way symmetry here. Okay. The distance between A and C deuterons is shortened as the B deuteron approaches A. This also shortens the distance between the C and B deuterons. Therefore, the deuterons are compressed into an extremely small cluster by the compression effect of the deuterons themselves. We call this the scramming effect. All right.
or you might call it bunching. I think the actual word is bunching, and he calls it in a later paper bunching, and I think this is the wrong word translation in this paper. The new version we have bunching, okay? The second stage is that the deuterons gather so closely that the iton can connect them. The distance between the deuterons is expected to be extremely short. The limit for the distance between the deuterons is 3,672 times the distance of internuclear distance. In this situation, the electrons move with the same velocity as the deuteriums. If the range of the new nuclear force is assumed to be correspond to this value, the rest mass of the iton is found to be 26 of the mass of the electron. On the other hand, as shown in figure 4, one or more electrons are pressed during formation of the NATO. We modify the Q value, blah, blah, blah. When the rest mass of energy is at 1 point, blah, blah, blah. This is because you're producing a positron-electron pair. A better agreement between the experiment and calculation was observed. The electron might need an antiparticle, e.g. a positron, to produce a mesonic iton. Okay, so remember what I said, in the center of the phase singularity, when you're causing magnetic colored confinement of baryons, it rips out a quark from a baryon, a proton, or a neutron, and the vacuum energy assembles for free the antiparticle, and that makes a meson. Okay, that is prima materia. He's saying that there is an analog of that in the electron, because basically quarks and antiquarks are leptons. Okay, they're charged particles, and they're leptonic charged particles with half spin. That is basically the same for electrons. If we're saying all these things are made of the same stuff, then you could argue that you could form a mesonic structure from a positron and an electron. So the electron might need an antiparticle, e.g. a positron, to produce a mesonic iton. And the 1.02 is 511 keV electron volts times 2. It's actually 1.022 MeV, it should be. Okay, so he's saying that 1.022 is lost in the production of creating this, but then the energy is then taken away from that. The rest mass of the iton is considered to be greater than 2 times the mass of an electron, which corresponds to 2.6 times 10 to the minus 11 centimeters of the range of the nuclear force. Therefore, it is supposed that the NATO is extremely compressed in view of the deuteron distance of this. Note the NATO is not a normal compound nucleus. Okay, so he goes on. It has been made clear that as a result of the hydrogen-catalyzed fusion reaction, the constituent deuterons of the NATO diverge with high energy. Since 2 deuterons are consumed per fusion reaction, it becomes possible for the deuterons to cause chain reactions in a metal if more than 2 deuterons are emitted, on average, in each fusion reaction. Based on this probability, we have discussed the physics. We have discussed the physics of a postulated cold fusion reactor similar to a fission reactor, where chain reactions are carried by neutrons. I think that should be, deuterons. It should be deuterons. But anyway, he says that. The feasibility of the emissions of a new particle, the iton, during hydrogen-catalyzed fusion reaction has been predicted by analysing the difference in Q between calculation and experiment. We estimate the rest mass of the iton to be 2 to 26 times that of electrons. So, he predicted what the reaction energy should be for the particles. He predicted what he should see out of experiment. He saw something from experiment. There was a discrepancy. The discrepancy needed to be adjusted by adding an iton. An iton was at least an electron and a positron, and that is what carries away the energy other than the other products of the reaction. Okay, so theory, prediction, calculation, experiment. Difference between prediction and calculation and experiment, and that accounts for this new particle, the iton, which is at least a positron and an electron. Okay. So I think Matsumoto should be credited with saying this specifically, and it is the cause of the energy in the de-excitation and so on. Where this model is more tested, in my view, than what is published here in this paper is that he went on to look at other things that were going on in this same experiment. So microscopic observations of palladium used for cold fusion. What did he find inside the electrode? But he found cracks at grain boundaries. And in there, he found that there were spherical sections that started to appear on the grain boundary and consume the palladium. And then after a period of time, these grew and they expanded out and merged into each other and ultimately led to the destruction of a whole crystal grain, consuming the grain. Okay, so starts at the grain boundary, grows at the grain boundary, joins up into a large macro stuff that then collapses and consumes the whole crystal of the structure. Okay, sometimes leaving behind little spherical blobs of stuff. This is where this work started to make him think of like ball lightnings. Okay, he then goes on. He thinks quad neutrons were working here because the NATO model produces this iton. The iton is converting the protons in the deuterons to neutrons, which means if you have two deuterons and they're both converted to both have their protons converted to neutrons, you end up with quad neutrons, and that goes through a process of gravity collapse. Okay, so this is how you would cause complete matter collapse. He justifies this by looking at the tracks on the emulsion in these diagrams and assigns them based on his experience of normal nuclear reactions, what these things must be that are coming out of these reactions. And this is something that literally no one in the field has this skill set to do. No one. And no one's even trying to have it, right? And so here's an explosion. And he's saying that, like, essentially this branch over here coming from the point of explosion out is a 4 hydrogen. That is an electron. You can see it because it's like scattered like this. This is also an electron. It's a higher energy electron over here. That is a proton. And this is a 3 helium here because it goes a little less distance. Okay. So these are cluster decays and so on. All right. So here we go. Heavy elements produced during explosive cold fusion, March 19th, 1991. So here he is. These are the elements. And this is what I showed you at the beginning. So in this same palladium deuterium experiment that he's referring all of his other work to here and his predictions, okay, that leads to the conclusion there must be a positron and electron carrying away the predominance of the energy from the excited 4 helium. He's seeing all of these synthesized elements. He's seeing 6 lithium produced. He's seeing the expected tritium and 3 helium that should be produced in the system to a degree, but he's also seeing all of these other elements, lighter and heavier. So palladium is in there, but where's the indium coming from? Where's the indium coming from? It's a heavier element than palladium. So just like Leonid Uritskev saw heavier and lighter isotopes of titanium, and he also saw heavier and lighter elements than titanium, here you've got palladium with a heavier isotope and a lighter isotope than palladium. A heavier element and a lighter element than palladium. Okay? And all of the usual suspects here are observed by Matsumoto in these structures. And so you see some things from gas spectrometry, and this was absolute genius what he did. Before he started looking at them under the microscope for EDX, he actually took the products of the reaction out and he put them in a chamber, which was a residual gas mass spectrometer, and he heated it slowly to 175 degrees, then for 775 degrees for an hour later, and then 775 degrees 2 hours later. So you can see more gases are coming out at the lower temperatures, and then it comes down to the background down here, okay, or the last gases to be coming out. So absolute genius. So this is not just normal reactions. For fluorine to be coming out, which he observed in EDS, and for neon to be coming out, this is much more than ordinary fusion, DD fusion going on. And these things, by the way, I would ask the researchers to also do this kind of residual gas analysis. You take your zirconium deuteride that's been impacted with the deuterons from the beamline, and you leave it, it's been doing all these fusion events for a long time. You immediately take that out as soon as you finished with it, and you put it in a heater, a special heating chamber where you can heat it up, and you have a residual gas mass spectrometer, and you look to see what you find, right? Will you find things that Matsumoto found in palladium deuterium? I don't know. I suspect you might. But if you don't look, you will not find it. You will not find it. It's true to say that you will not find something if you do not look for it. Well, it might fall in your head, but doubtful in this circumstance. You do not look for it, you will not find it. Then in your head, you can think you're true about what you think is going on, right? You can believe, you can maintain that belief structure. But we need working technology. We don't just need a bunch of belief structures, okay? Look at the gas, look at the elements on the sample. If it shows products that are in line with the rest of the field that bother to look, then maybe it isn't just deuteron-deuterium fusion to 4 helium excited producing a positron-electron pair, which would not allow you any recoil products or structure products to allow any reactions. Okay. Bearing in mind, I'm looking at this from the magnetohydrodynamic point of view. This may be going on in the core of one of these magnetohydrodynamic structures, but whatever. This is the early work of Matsumoto, and he's already calling this positron-electron production out. Or, that's what he's saying. That's what he's saying. That's what he's saying. Okay? What is doing the crushing is open for debate. But what he's saying is that these things are coming out, and I think he should be given credit if it turns out to be true. Okay. Is there anything else? He found gravity waves. Yeah, gravity waves coming out of there. And what else? What else? I think that's probably it for this today. But as I said earlier, in various cold fusion experiments, which granted are not metal and deuterium alone, you do find structures that can capture material and spit it out after it's processed it, and it is often larger than the internal volume. So there's obviously some compression going on of some kind of compression is going on, and after it's compressed, other elements are formed. It looks like there's a little bit more interesting than just a physical compression. I believe it's a compression that's based on magnetohydrodynamics. And all of the elements you see typically out of these products are, of these systems are produced in cavitation. And in Matsumoto's 1991 work, this is the paper I've just shown you, both the standard fusion products, the tritium and 3 helium, as well as 4 helium here, okay? Of course, that has the same mass as D2. But also he's seeing 6 lithium and potentially 6 helium or D3. But also heavy gases like neon potentially and fluorine is confirmed by EDS, magnesium, aluminium, silicon, phosphorus, and all of the normal elements we see, which are also seen in Ficcardi Piantelli 1994 nickel hydrogen with a structure that's doing the magic, like we have seen and we've seen in various systems, and like in a water flow plasma discharge was seen by Bogdanovich et al. Working with Nestorovich in the Moscow Nuclear Physics Institute. And that would explain from this hole spurting out of the back what is observed by Matsumoto. This is not 4 helium. This is larger proportion of this is carbon coming out of a lead ball. Okay, so we also showed that in titanium deuteride, exploded foils, you get isotopic anomalies where 48 goes down and all the other isotopes either side of it go up, and either side of titanium you get heavier and lighter nuclei formed. Okay? I suspect that if the authors, Mr. Dubé, Mr. Chersky, Dazh, Kowalska, Targosz Śledźka, Kaczmarski, sorry, my Polish pronunciation is terrible, and Mattia Velat, if they choose to look at their samples, they will probably see, if they've been run for a sufficiently long a time, producing sufficiently large amounts of excess energy, it is my belief that they will see transmutation to other elements. That is my view, and if that's the case, they might need to consider different channels for explaining the observable data. Okay, with that I will say that's what I've got for you tonight, and I will ask you therefore to ask me some questions. Before we go and ask some questions, I just want to remind you to go out and please do this. And it will, if you do it, then it will be picked up in a number of days. And I think it's very, very important at early times of papers to do this. You need to go and report onto things like your social medias. So on X, on Reddit, on Facebook, if you've got a personal blog. And what you must do is you must reference the name, ideally, but very much at least this HTTPS and the DOI number here. You must reference that and make some comment. Go and have a look at this paper or whatever it is. I haven't asked you to do that for my paper. I won't stop you. I won't go out there and say, please don't do this. Please don't do this for my paper with Binja and Huang. Don't do it. Just don't do it. I'm not going to say that. But I am going to say, please can you do it for this? Because it's flatlined already after the second day, after it was released, and we want to get more exposure for this work. I hope then that they will be able to go to the European Union and ask for some more money, and I would ask them to spend the first money that they get, if they get any more money to do this research, the very, very first money that they spend is to look at their target samples. See if there's any gas coming off them, use the Matsumoto method, and then see if there are any new elements or any new arrangements of elements that shouldn't be in there. And if you claim that it's because the zirconium, in your case, was, how should we put this, contaminated, it's contaminated, then be better with your procedures. And if it's contaminated metal in the first instance, then you're going to have a problem. You're going to have a problem because you don't know where the nuclear reaction is particularly coming from. Because it might not be something that the zirconium is doing. It might be something that some of the contaminants are doing, or the particular interplay between the different contaminants in there, right? So hopefully your zirconium is really, 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 really pure, and that's all you've got. And if that's the case, and you handle it properly, then spend that first bit of money. And if you can't bring yourselves, you can't find the desire for what is actually going on, or the desire to add weight to your own proposals. If you can't find that, then I am willing to do it for you. I'm willing to take those samples, or to have you bring them, maybe I can even raise the money to pay for someone to come on the train from Szczecin, or drive 6 hours down, and we'll put them under the SEM, or rather you'll put them, I don't want to touch them, don't let me touch them, you touch them, and you get that sample, you take it out of your ultra high vacuum with under special conditions, you put it in your sample container, you bring it, I'll try and find the money to pay for the travel, even somewhere for you to stay, right? You put it in the testing device, we record the whole thing. You taking it out, you putting it under the test device, us doing the measurement, and we'll see if the sample is still ultra pure zirconium. Let's do that. Why not? So you don't have to pay for anything. If you can't find someone to come in the car, I suggest you do the proper packaging procedure, you have it shipped. We'll pay for the shipping, okay? Tracked, signed for, okay? And then we'll video the unwrapping of the packaging and videoing the whole process of unwrapping the packaging and putting it into the sample holder and it going into the device, okay? Right? We'll do the whole lot. You will see the whole lot, right? No funny business. No funny business, right? And then we'll see if there's no changes on there. Because your theory says there will be no changes on there. It'll be pretty unique in the field, from my view. It'll be pretty unique. But might happen. Who knows? Okay. All right, with that, I'm going to ask if there are any questions. Are there any questions? I know this was a very different one, but it's very rare that we get a paper, one, in a major journal, two, in a major journal that's been funded by the European Union to create, and three, making a bold claim about how a particular reaction might occur in the field of condensed matter nuclear science. So there's a lot of big things going on here, and it needs more analysis and more consideration. All right, so I'm going to look through your chats. First off, I want to say thank you to all of those people that donated tonight. It's absolutely fantastic. Thank you to Black Tie for your £20 and your further £20 and your yet further £20. That's 3 lots of £20. That's absolutely amazing. I think now we've definitely got enough money to do a control test on the test, which I was going to talk about radiation remediation today. I was going to talk about that, experiments that we've done, but this came up and I wanted to address this paper by the European funded team and by Matthew Vilat et al. And Rakesh Dubey and Konrad Chersky's theory here. I wanted to address this first, and I wanted to first, I was going to even address this the following day, but I thought, no, I'll give them 5 days to answer any questions that I could raise that were sensible, and to see if they would consider Matsumoto's work. They completely dismissed his work and they didn't answer a single question at all. I even said to them that they can join in the chat today. I gave them notification so that they could be part of this conversation. I don't know if they've joined in. Maybe people have noticed someone commenting in there. But I think they treat the MFMP and myself with utter contempt. Certainly the questions given in conferences seem a little bit like that might be the case. That's a shame. In the last 6 years, they've had probably around about 10 times the amount of money that the MFMP has spent in 13 years in total. It's a shame that they, who are their peers? They're obviously going to agree amongst themselves because this is the work that they've done for 6 years, right? Whatever. So who are their peers? Well, I don't know how many people out there at Physics Review can have a judgment about this. I don't know who the peer would be reviewing this. I'd like to know who the peer reviewers were. I guess the idea is that if you don't mention transmutation and you only use something that's accepted, which is internal pair production called pair creation by Chersky, then you're not going to ruffle too many feathers with electron screening, right? So you're going to get it published and no one's going to ask too many questions, right? But there is a history in the field and you can't ignore it, okay? So thanks again, David Ellis, for that $9.99, John L for that £10, and wow, Scoggy Hoggins, very, very appreciated for that €50 contribution. That's absolutely amazing. All right, so hopefully you've got some questions for me. If not, good night, Jalapeno. Will plasma energy ever replace electricity? If so, how would it be transmitted? plasma energy. I would suggest that plasma toroids in neutral form can be shifted by an electronic gradient over very thin wires, and this has been a proposed method for transmission of energy. It was proposed in part by Avramenko, and he demonstrated it. Plasma energy, I would suggest you are able to potentially synthesize electron-like clusters or electronic vortices from matter and or relic neutrinos using forms of plasma and the products that they produce. Then those electrons can be used in the same ordinary ways. I think these type of power systems I would see actually embedded into the devices that would use them. That be, for instance, a ground or air propulsion or transmedium propulsion device that would take you as a passenger. So I don't think there would be much need for transmission of power, because most of the power you'd ever need would be in devices that you would be using, devices or transportation mediums, or in machines. The machine would have the power in it. Simeon Hine wrote up a nice list of lender history. Oh, great. I'll look forward to seeing that. Simple Man says, do you know the US purposely pays these European scientists to divert these studies so that the US can keep all the tech and patents in the US? You redcoats and the French are thieves, sold out your country. I am aware and was told specifically that an American individual came over and told, you know, was principal or main player in deciding who got what and for what. So I'm pretty aware of it. I'm also aware that the other project was told not to speak to me or work with me, and then I suspected something weird was going on, and then on the day that the contract had finished, the leader of the second European project phoned me up asking me to come and meet all of the people of the second European project to give a lecture to them and then to have dinner with them. I couldn't do that because I was releasing all of the Thor videos that I had outstanding to get those out the door so people could evaluate them. And that was called Thor's Day. So it was that day, we know which day it was. And I then went to dinner with them, and the leader of the second European project apologized for 2 hours straight. It was the most weird thing to have experienced, and he said he was told not to work with us. Simple Man says, come over there. Well, I have been invited to go to a facility in the US, which when you try to look at it using Google Street Map, you can't. And then I found out it's a off-limits secret facility. And I've been offered to move there and live there and move my whole family there, and I've alternatively or also been offered to go over and regularly as a consultant, and I haven't even responded to that email. It's so far removed from who I am, and given the people involved, I don't know, but they're in a position to ask for very large amounts of money from Congress. That is their claim, and the location is this location, and you know, that's just not me. DIY projects with Chogsis. Oh, come and visit us in Australia. That is very tempting. Only if you take me out on a nugget hunt.
So John L says, is it compression via fusion, or is it compression via smaller distances between particles due to the changes in the normal forces of electromagnetism? I've argued, if you want to go and see what I think it is a ball lightning based process. It is a fractal magnetohydrodynamic process which leads to a fractal toroidal moment. That fractal toroidal moment has a phase singularity at its center and fractal centers. That produces a increasing magnetic field in a ring singularity. That produces a Blake spheroid or an apple-shaped event horizon. The eventual outcome is that the center gets such an intense magnetic strength that is able to pull in the medium over which light travels, that is clusters of relic neutrinos, so fast that the light cannot escape, because it's being pulled in with the medium in which it's trying to travel faster than it can escape, and that leads to the thing which we call a black hole, because the light can't escape from it. And this produces, between that phase singularity and the boundary of the electrodynamic structure, a gradient in the ether, where you have the ordinary 0-point vacuum energy, vacuum state outside, and that is a gradient between there and the center of the phase singularity, which effectively is a Casimir well. That is to say, it's a continuously closing Casimir plates, right? Because when you go push together, you're reducing the photons that can fit in the gaps, and so you get push from the outside. But if you're always removing the photons from the immediate vicinity of the phase singularity, then you're constantly getting the other photons, pushing the other photons towards the phase singularity. So this results in a flux of photons through ordinary matter of all wavelengths, which excites it. So in part it's excitation, and in part it's because of the magnetic forces, and that leads to everything from van der Waals to Casimir to hydrogen bonds to polar bonds to covalent bonds to ionic bonds, then covalent bonds, and then through decay of beta particles, alpha particles, cluster decay, strong nuclear force, strong interaction, and I'm not sure on the order of that off the top of my head, and ultimately to quark-gluon plasma from magnetic color disconfinement of baryons. And that's all in my ICCF 26 poster presentation, which you can download. So that's what I believe is going on, and some part of that will be crushing your deuterons together, and maybe it's doing what Matsumoto is observing. Certainly what I have said there would lead to all of the different products that you see coming out from a relatively simple mechanism. Yes, Matt Bartelson, scale invariance. Compression via resonance and frequency, yes. Faye Clegg, yes. You only have 4 wonderful nuggets. You know what? DIY with Chalksis. If you don't look, you will not find. If you are chicken, that is to say, you can't be dared into doing something, right? You're not going to find the little golden egg, are you? You're not going to find it, right? So you just need to get out there, my friend, and do a little bit more prospecting. Okay. Contraption, don't make with the deal with the devil. No, that ain't me, mate. That ain't me. You know, there's a lot of things that can make you happy in life. Actually, no, there's only a few. And it's mostly family. Family, friends. I think probably health. Health, family, friends. You can't be happy for anyone if you're not healthy. And yeah, I hate flying as well. I really hate it. Faye Clegger said, why did the chicken cross the road? Because it wanted to get to the other side. Haha. God was first, simple, easy, undeniable. Yes, I'd agree with that. Intent. The great intent leading to the great work. Are aliens real, and is Uri Geller real? Ah, well, these are some good questions, Simple Man. It's, in my view, absolutely 100% certain aliens are real. I used to think Star Trek was not having a proper prosthetic budget, but on retrospect, I believe that the humanoid form, pending chemical and environmental and standard temperature and pressure on a particular evolution location, and whether it's predominantly water or waterland or land-based, will predispose the answer to the program to look a bit like us with variation by aforementioned variables. And so I don't think they were. I think they got lucky, or they knew something. Fake says, melted steps in the pyramid, is that a result of plasma Lena Evos? You could argue that all melted things have got movement of electrons, and therefore there's kind of like, do they become conductive? We know that silicon dioxide becomes conductive over 1,000 degrees. So if it's melted, because it melts, okay, so fused quartz melts at 1,706 or something, 1,700 degrees over. At that point, or over 1,000 degrees, it already becomes a conductor, okay? So it depends how high the temperature is. Like alumina becomes a conductor over 1,000 degrees, something like that. It's the basis of the Nernst lamp, N-E-R-N-S-T. This is before they invented filament light bulbs like the tungsten filament light bulb. They would heat a piece of ceramic up over 1,000 degrees, and then they would turn the electricity on. And if it's able to pass electricity, then the electrons are free to move through the material. So technically it was a solid plasma, a bit like a metal is. That's probably not the question answer you wanted. Right, so Korki said, how is the new edition of the Taki Matsumoto book going? Must be a thrill, archivally speaking. It's hard work. I enjoyed my understanding and expanding my understanding of Matsumoto's book in the review of this paper this week. I do hope to get out the PDFs to everyone this month, and that is my goal. My wife is back at work, and so things are in a better position for me logistically. So John L says, are you saying the Earth is not the result of a supernova cooked elements, but rather that the Earth formed from hydrogen gas and the rest of the metals are a result of many years of this process? I would suggest that the Earth started with a whole bunch of material, but that it's a living organism and it continues to create both matter inside its core and matter in its geological processes and directly on the surface through other physical and geological processes. Specifically, Coriolis and magnetohydrodynamic effects in the core lead to capturing and condensation of neutrinos from the cosmos. This is a model of gravity where that becomes effectively a gravitational well, and that higher up in the crust and in the upper mantle, there are further ball lightning kind of effects going on, and low energy nuclear reaction and these kind of effects. And they are leading to the synthesis of other elements that we see coming out of volcanoes. And then on as water and other stuff are exposed to the heat generated from that, this moves through cracks in the rocks, supercritical water, and then it becomes cavitates and stuff as it moves through different cracks. This produces other synthesis of elements, producing to enriched hydrothermal elements coming out of hydrothermal vents, and similarly on land.
and that also cavitation in water crashing on a shore, running down a stream, would produce elements, and I believe that's why life likes to live near moving water. And lastly, the how should we put this? Electric discharges in the environment, including those in the form of lightning and ball lightning and other long-lived luminous objects in the upper atmosphere, are all synthesizing elements. And then lastly, there's a little bit of a contribution of flux and fields and particles from the sun, which kind of feeds into the process. Hi, David Boutelier, and Thanksgiving from the UK, but it's not something we do here. So Corky said the Earth is a pornfessional star across the galaxy. Jon does live. Many authors, including I would cite Leclerc in cavitation, and before him Kladoff in cavitation, have shown that all the elements appear to be able to be produced by cavitation. Cavitation is charge separation, magnetohydrodynamics, and producing the effect. And in the case of plasma discharges or high intensity electrical discharges, S.V. Adamenko produced all of the elements in the periodic table and some that do not exist in our near universe. And so, yes, you do not need supernova. Okay. All right, so this was, how should we put this? This was positron, electron, chicken or egg. I'm asking the authors of this physical review X paper to test to see if this really is what they hope it is, which is a definitive mode of DD to 4HE reaction channel, by doing the work necessary, that is to say, running an experiment sufficiently long such that there is meaningful potential for observation of anything else going on in the sample, and then do proper analysis both spatially, gas-wise, and elemental and isotope-wise of those targets, to see if there is anything other than slightly abraded, beam eroded, crystal grain boundary, thick fractured zirconium on there. If there isn't, I suggest you need to have a rethink about your postulations in here. Regardless, I think that you need to credit Matsumoto, who said essentially that if you see a positron and an electron annihilations going on in your experiments, then possibly that is all that's necessary to take the energy away from the excited for helium. And if you don't, then maybe you need to have a neutrino in there. I could argue that if it's a basic exotic vacuum object that's coming out and it gets excited by the aluminium in front of the detector, or as it transitions through a window on a detector, that maybe you're then seeing the breakup. I don't know. I just think more work needs to be done before you can make the claim that this is a discovery. But it's good work, and thank you for all that you've done over the last several years to get this out, and thanks for representing the field and getting it into a sensible journal. And I'm going to try and see if the guys out there can do the job to get its exposure up. So, thank you very much for your time, and I will see you in the next video. Buenas noches, dobranoc, good night.